Okay, good morning, everyone. Let's start. So hopefully everyone has enjoyed a great long weekend, Labor Day, right? So, but here we have to announce that we will release homework 1 today. And after today's lecture, you should be able to start homework 1, which is all about decision tree algorithm and implementation and testing. We'll have both paper problems, which deepen your understanding of this ID3 algorithm, which we're going to discuss today. And also like 2 data sets with which you can run and test your implementation of ID3 algorithm and see if they can give you some reasonable performance. But again, I highly suggest, although I repeat this numerous times, I highly suggest you to start looking at those problems today. Maybe start working on it tomorrow. So don't wait until the last day or last minute, especially for programming portion. You won't have enough time if you just want to finish it in 3 hours, because you do need some time to debug that. Although you might feel like you really understand algorithm details, but when you implement it, you will always find some problems. It's more problems, more like in debugging, coding those issues rather than the logic, the algorithm logic. Right? So again, please start early, and again, please leverage the office hours and try to ask questions either in office hour or in on Canvas. Okay. So let us resume from what we discussed at the last lecture. So we said that we're going to use this example to illustrate our ID3 learning algorithm. As we mentioned, ID3 is the most classical and most popular decision tree learning algorithm. So this particular example or task is to predict whether I will play tennis today according to the weather condition. So we're going to use 4 attributes or features to represent the weather condition every day, right? We use outlook, temperature, humidity, and wind. And the outlook can take 3 values: sunny, overcast, raining; temperature, 3 values: hot, mild, cool; humidity, 3 values: high, normal, low; and wind, take 2 values: strong and weak. Again, I mean, to simplify, for simplicity, we assume all the attributes are categorical, but later we're going to discuss how to convert the numerical features into binary features or categorical features, and then apply our ID3 algorithm. So we have collected the weather conditions and my decision to play or not play tennis in the past 2 weeks, namely 14 days, right? So 1, 2, 3, 4 to 14. And every day we have recorded the attribute values and my decision, right, which is a binary decision. And here, for simplicity, we just use the capital first letter of each attribute name and attribute value to represent the data, right? So as we mentioned before, right, the decision tree learning essentially is a recursive procedure to hierarchically partition the data set into smaller and smaller subsets. At the same time, we're going to create new tree nodes and new branches until all the subsets can be viewed as some kind of leaf nodes, right? And also, so this is kind of a hierarchical procedure, a kind of recursive procedure. So here we just showcase the learned tree by running ID3 algorithm. We're going to discuss in a minute. And so you can see that the tree only has 2 levels. At the beginning, our ID3 algorithm will pick up this outlook attribute to split data set, because outlook can take 3 possible values, right? Sunny, overcast, and rain. So it will grow 3 branches where each subset are examples which take a particular value of the outlook, right? And you got sunny examples, you got overcast example, you got rain examples. And then for sunny and rain subsets, we further use humidity feature and wind feature respectively to split on them, right? And then we arrive at leaf nodes for all the subsets, and then we'll finish tree construction. Right? So this is just to give you the running result of our ID3 algorithm. So now we would like to say how this tree is constructed under the ID3 algorithm steps. Right? So sorry. So basically, as we mentioned, right, the tree construction is a recursive procedure, right? So for the convenient algorithm design and implementation, we're gonna develop a recursive algorithm for the tree learning called ID3, right? So the input variables to ID3 consist of 3 parts, right? The first one, S, is the set of examples, right? So you can imagine at the beginning, this set of examples is the whole data set, right? And then because it keeps calling itself to recursive partition data set at some middle stage, S might be just subset of examples. And the label is the target attributes, namely the labels or predictions associated with each example in S. Then the attributes is the set of attributes which we're gonna use or select to split the data in S. Okay. So you can imagine we just use one call, like ID3, the whole data set, the whole attribute list, of course, the all labels. But then we run ID3. We're going to split the whole data set into small subsets and then call ID3 again. That is recursive programming, right? It calls itself to further partition each subset and call itself. So you can imagine through this recursive calling, some new tree nodes and new branches are growing, and correspondingly, those subset of examples are further partitioned until we believe that, okay, this subset should be viewed as some leaf nodes. Then we'll stop the further partitioning, right? We'll finish all the partitioning of those subsets. We have finished the construction of the tree. So this is kind of an overall impression I want to give you. But first, if we want to design a recursive program or recursive algorithm, I would like to ask your thought, right? What kind of things you should first consider? The base case. Okay, so can you, I know what's your point, right? So can you explain it a little bit more, even more straightforward? Yeah, exactly, right? Exactly. So how many of you have done the recursive programming before or heard of them before? Oh, okay. So basically recursive meaning that, okay, I can construct a right line of code, right? And allow this line of code to call itself and to do itself. In the computer science domain, it just means the implementation of recursive programming is to use the stack space. So when you call yourself, actually increase the stack pointer and to store all the information of the current calling and call yourself. But you cannot keep calling myself forever, right? If you keep calling that, if you do not stop at some point, you're gonna exhaust the whole stack space and you're gonna make your program crash or make your system crash. So whenever we design a recursive algorithm, the very first important step we need to think about is when we should stop the recursive calling, right? That is what he said is a base case or namely when should we stop, right? So now, in our case, in which cases should we consider, okay, we do not need to call ID3 anymore? Okay. Yeah, that's very, very comprehensive, even beyond ID3. But I mean, that's a good point. Any other supplement? Okay, that's good. Yeah, I think you're totally right. And but that's what he mentioned, right? So remember how ID3, the goal is to expand the tree, right? And grow the tree. And when you grow the tree, that just means, okay, for some subset, you're going to further split them into even smaller subset of examples, right? And so that you can create new branches, you can create the new nodes. And when should we stop that? It just means, okay, we have matched the leaf nodes, right? When we view like, okay, the current subset should correspond to a leaf node, we should stop, right? So that's where we should stop calling ID3 anymore, and we should return. So when should we will the ID the current subset as a leaf node? Yeah, exactly right. Actually, he has mentioned that. So when we do this manually, when we did this manually, right? A simple criterion will be, okay, if currently all the examples in this subset is unique label, right? It has the same label, then there's no necessity to further partition, right? We should stop and reveal, okay, this subset should be a leaf node, should correspond to a leaf node, and we just assign the label as label for that leaf node, right? So that's our stopping criterion, right? So remember, whenever we want to write or design a recursive algorithm, we need to first consider which is the base case or which is the in what kind of cases we should stop. Right? So in here, the very first stopping criterion we should consider is that, okay, if all the examples in the current S have the same label, then we return leaf node with the label, right? Here, I want to emphasize another boundary condition. That is, if the attribute set is empty, we have to stop as well, right? Why? Yes, exactly, right? So if it is possible, right? Suppose you have 1 million examples, but you have 10 attributes, right? It is possible that no matter in which kind of order you use those 10 attributes to split data set, even if you used up all those 10 attributes, you still cannot have your subset of examples to be uniquely labeled, right? In this case, we don't have any more attribute to further split on data set. We have to stop, right? So this is like a corner case. And if we don't consider that corner case, it is possible it is possible like in 50%, in 60% case, okay, your algorithm runs, no problem. Everything looks good. In some cases, your algorithm just stopped or crashed or stuck there forever. You don't know why. Right? So this should be real careful, especially in practice. If the current set of attributes is empty, meaning that all the attributes have been exhausted to split the data set, right? And then you don't have any attribute to further split S, you have to stop and have to return a leaf node. And I'm gonna use the most common label in S as the label for this leaf node. Does it make sense? Yeah, that's a good question. So as we discussed in the last lecture, right? So when we have the numerical feature values or continuous features, we're gonna first convert them into some categorical features. So then we're gonna get rid of those original continuous features and plug in this converted binary or categorical features, and then perform all those. So this should be the cases, like most general case. Well, you still cannot exclude the case that, okay, you have exhausted all the available attributes. So by the way, is everyone comfortable with this? Everyone's feel good about this setting of the stopping criterion or boundary condition? Mm-hmm. Yes. We're going to talk about it in a minute. Right? So every time when we use attribute, we have to exclude it. Why? Because we use that attribute to split data set, right? You can imagine each subset will take exactly the same value of that attribute, right? If you use that attribute to split again, you can't split anything, right? Because all examples share the same value. Okay. But we're gonna reach to that point later. Okay. Yeah, if everyone is comfortable with that, okay, that means we are successful at the very first step. Okay, we have set up a good boundary, good stopping, or good base case to ensure that our ID3 algorithm can stop at the appropriate point and then return, right? And then if the stopping criterion or the boundary condition is not met, right? Meaning that we might still be able to partition the current subset of S, right? Subset of examples S. So how can we do that, right? So first, we're going to create a root node for the tree. This root node corresponds to S. Remember, in the tree, decision tree definition, each tree node is associated with a subset of examples, right? So if this is our very first core of ID3, meaning that S corresponds to the whole data set, then this root node, meaning the global node of this tree. Okay? However, if S is middle, meaning that, okay, I call the whole data set, whole set of attributes and label set, and then do some recursive calling, so you might arrive at some middle stage. Then we know that S corresponds to some subset of examples, right? Then now the root node corresponds to the root node of the subtree. Does it make sense? Okay. So we're going to create a root node for the tree which corresponds to the current subset S. It could be the global root node, or could be the root node for the subtree. And then from the available attributes, from this attributes variable, right? We're going to pick up a attribute A, which can best split S. Right? So far, let us consider we have some specific procedure which we can select best A, right? But regarding what do you mean, what's the meaning of best splitting S, we're going to discuss about it later. Right? Now let us just assume, okay, we have some specific special procedure which can identify the best attribute A from this list of attributes, right? We pick up A, right? We're going to use A to split S. Now, how can we do that? We're going to enumerate every possible value V that A can take. Right? For each possible value V that A can take, we're going to create a new tree branch. in this branch, we're going to attach a testing condition to test if the value A is V. So remember, this matches the tree definition, right? For each branch of the tree is associated with the testing condition, right? So we're going to enumerate every possible value that attribute A can take, right? And then create a corresponding tree branch associate or attach this testing condition. Right? So of course, along with this tree branch, we have a subset of examples in S, where each value in this example takes the A attribute value to be V. Right? So we denote this subset of example by SV. Right? So this is basically a kind of formal description that I'm going to use A to split on S. Right? So each subset of examples will take a particular value of attribute A. Right? So we denote this subset by SV, right? Because V indexes the attribute value V. Right? So is everyone good? So far, so good? Okay. So now we should consider some cases, right? So first, what if SV is empty? So basically it means, okay, in all the examples in S, no one takes the attribute A's value to be V. So we end up with an empty SV, right? If SV is empty, how should we handle this case? Right? We shouldn't consider branch. Yeah, that's one intuitive option, right? Any other suggestion? Add to one of base cases. Yeah, you're right. That's another choice, right? But for the base cases, would you like to okay, I'm gonna remove this branch, namely A equals to V, or we do something else? So I mean, you're gonna still append a leaf node, right? Average values of attribute. Okay, no problem. Because here I want to emphasize this is a categorical attribute, so it's really not very sensible to average their values. Any thoughts? Return the result of parent node. So what's the meaning? Let me understand what your meaning is. So you mean you're gonna create a leaf node and return what? Or you want to remove this particular branch because it's gonna give you an empty subset? Yeah, but what's the meaning of the parent's result? So okay, so your result is actually meaning the label, right? The prediction label. Yeah, okay, I got a point. Thanks. So thanks for providing all your thoughts. It at least suggests that everyone is, is on the same page. I'm very happy. No one is lost, right? Everyone is happy at this point. Okay, so here I want to give you the ID3 algorithms design. So even SV is empty, in the implementation of ID3, we're going to still preserve this testing branch, and we're going to add a leaf node. Even associated with this leaf node will be an empty subset. And then what is the label of this leaf node? We're going to choose the most common label in S. We use that most common label in S as label for this leaf node. So now it's time to ask why this is the case, right? Why this is the choice of the ID3? Yeah, exactly, right? Yeah, okay, yeah, great. So now everyone kind of like recall what you have discussed before, right? So let us review this manual tree construction case we did in the last lecture, right? So for this set of labeled color shapes, we manually create a decision tree, right? And following kind of a similar procedure as ID3 does. But here, when we want to further split on this green shapes, right? So we notice that all the existing green shapes, they either are squares or circles, right? There are no triangle green shapes. So intuitively, we just do not create a branch testing if the shape is triangle, right? And we don't create the corresponding leaf node either. Then what is the problem? The problem is that, okay, when we have a test case, which is green triangle, we are not able to provide any sensible prediction, right? That's actually not allowed, right? You can tolerate the inferior performance of your classifier, but you cannot tolerate that, okay, it's just stuck or not being able to give you any answer, right? So we have to make our algorithm to be robust enough. How can we do that? By following the particular step we just discussed, right? So even at this stage, when we use the attribute value triangle to split this subset, it is empty. We're going to still create a branch and a leaf node, right? And of course, the associated subset of this leaf node is empty, right? But we're going to still assign a label on that. And this label is chosen as the most common one in its father or parent node. Does it make sense? Is everyone comfortable? Okay, that's why we use this special line of code to deal with this corner case. Otherwise, your implementation of ID3 will have the embarrassing case that you are not able to provide any sensible prediction. Okay. So here we just give a brief emphasis again, like this is for generalization at test time to ensure that you are able to cover all possible test cases. Okay. So, okay, if SV is not empty, meaning that, okay, there are a bunch of examples in S which whose attribute A takes value V, then things becomes a lot easier, right? So we're going to consider further partitioning on this subset SV. So how can we do that? We call ID3 again, right? This is a recursive call. So we call ID3 again, and now the input are changed to, like, the subset now becomes SV, namely all the examples in S whose attribute A takes value V. And then the attribute set, available attribute set, should have A removed. Why? Yeah, we have already used A to split on data set, right? So you can imagine, you can see that all the examples in SV whose attribute A takes the same value V, right? So it's meaningless to use A to split again, because all the examples in S, if you look at their A values, they are the same. They all take value V. So if you use A to split them, how do you split them? And then you can imagine, okay, by using this set of inputs, you call ID3 again, you're gonna consider, okay, first, if SV, this new current attribute, available attribute set and labels, if they have satisfied base cases or stopping criterion, meaning that, okay, if they're, it should be viewed as leaf nodes. If it is, okay, we stop and we finish, right? Otherwise, we're going to create a root node for the subtree and then pick up a best attribute from the current available attributes and further split them, and then consider to look at each splitted subset and call this ID3 again until all the subset, when we call this ID3, they have matched the stopping criterion with leaf nodes, and then you just return, and pop up all the stack species you finished the tree construction. This is overall algorithm design. It's very concise and simple, as long as you don't feel uncomfortable or feel sick of this recursive programming framework. Okay, any questions so far? Here? Okay. Yeah, as we discussed, right? We're gonna use the most common label in its parent node. Oh, okay. Okay, that's a good point. So so we got 4 green shapes, right? 2 label B and 2 label A. So here we have ties, right? We got equal number of the labels for B and A. In this case, if you don't have any prior preferences, you can choose arbitrary, right? But if you have some arbitrary, okay, if I have some preference, okay, I will believe A is better, then you can use A. Otherwise, if you don't have any prior knowledge, you can choose any, because from the data itself, it doesn't reveal any, preference. Okay, let's go back to this ID3 algorithm framework. I want to ask if everyone feels comfortable with this framework. Okay, so I'm gonna use my use some kind of drawing to simulate the running procedure of this ID3 to give you some kind of impression, in case that someone still feel a little bit. You mean this one? That's a very important part of talking. We're gonna talk about in a minute. Right. This is very important. But first, let us try to understand the whole framework. Okay. So here I want to just give some kind of random simulation for running running ID3 to give you a sense how this algorithm is executed. To give you a sense, in case that someone might still feel a little bit less concrete about recursive programming, right? So, but if you have some experience of implementing tree traversal or tree construction, those basic data structure topic, you should feel totally fine about that. But in case that, so please bear with me. So you can imagine, like at the beginning, okay, I got this big data set. This corresponding big data set. This is my first calling of ID3, right? I got like maybe 1,000 examples, maybe 50 features, 50 attributes, and got those labels. I called ID3, and of course, I'm going to first test if all the examples have the same label, which is rare. It's really not possible. So usually we're gonna go to this part, right? We're gonna create a root node for this tree, which corresponds to the whole data set. And then we're gonna pick up the best attribute A from the current attribute set. We split this whole subset into several subsets, which correspond to several like branches, right? You got several subset, right? And here in the tree, it actually corresponds to several nodes, right? Several nodes. And you can view like this could be SV1, right? This could be SV2. You know that each SV1 is the subset of examples whose attribute A takes the same value V1, right? So now, and of course, if some attributes, some subset like SV3 turns out to be empty, well, you have to create a leaf node here, right? Create a leaf node here and give a label, and which is most common label here, so it's fine, right? So and then if we take a look at SV1, right? If we want to further split down SV1, we're gonna, oh, sorry. Sorry, I should use this slide, right? So this is one. So suppose this is some empty, right? This is some intermediate node, right? So this is SV1, and this SV1 is not empty. So we're gonna call this ID3 algorithm again, and now the input to this ID3 will be SV1, like this subset of examples, and also the attributes will have the splitting attribute A used before excluded, right? And we call this algorithm again. Now you can view that, okay, you look at this ID3 algorithm and run it again, and under this SV1, right? And then you first check if all the labels in SV1 are the same. If they're the same, okay, SV1 should be viewed as leaf node, which is not right. Otherwise, you're gonna create a root node for this tree, for this subtree, and then you can pick up an attribute to split SV1, right? You got a bunch of other subsets, right? Which I'm not gonna write it out, but it's just a subset of SV1. Each subset of SV1 will take the same value for some splitted attribute, right? And then we just look at each subset, right? If this subset is empty, now you create a leaf node, like following this line. Otherwise, you call ID3 again to split on this subset, right? Following the same procedure. So you can imagine, for example, at this stage, right, when you call the ID3 to split this subset, you find that, okay, all the examples have the same label. Okay, you return the leaf node with the label, right? So now you return back here, right? And now you look at the second subset here, right? You call ID3 again. Now you try to split this subset. Suppose this subset, all the examples have the same label. You got the leaf node. You finish the tree expansion. Now you return from here. And then for this guy, and this guy suppose is empty, just stop here. So now you finish the recursive calling at this level. Now you return from here. And now you move to the next subset of examples which are splitting on A. Okay? Remember, this is recursive calling. It's gonna catch all the previous stage. Okay? So at stage 1, you got SV1, you split them on them, you finish split SV1, you're gonna move to the next subset, which takes another ace value. Okay? So you're gonna recall this attribute, recall this ID3 algorithm again, you try to split them maybe several times, and then finish the splitting. Then you return this ID3 call, right? And now you move the last subset, which take the third value, for example, of A, right? And now you recall ID3 algorithm, maybe, or it's just because the SV is empty, you just finish the construction, then you finish the calling of this ID3, now you return to the root calling, or very first calling of ID2. There's a whole, like, one example of execution of this recursive program, right? But if you have had some experience of like tree construction, tree traversal, this wouldn't be a problem. It's very natural. However, if you still feel a little bit confused, uncomfortable, I'll suggest you to look at some like very quick tutorial about the tree traversal, tree construction algorithm in data structure. It's very easy to understand. and you know what exactly I'm talking about. Okay. Anyone? Is everyone comfortable? Everyone is good? Okay, yeah. So now we want to address the last question in this ID3 algorithm implementation, namely how to pick up the attribute to split, right? So in our framework, every time, okay, we want to pick up attribute to split on the data set, we assume that we have some specified procedure to split on this data set, right? We haven't get to the detail. How do we select? Right? So now we want to illustrate this problem, right? So how to pick up the attribute to split, right? This should be associated with our goal, our overall goal, right? So this actually has been discussed in our previous lecture. Suppose we got the same data set, right? You got like you got multiple trees, right? Each tree can well represent this data or well partition data. Now, which tree would you like to prefer if you are asked to select one tree? But all those trees are equally well can equally well represent the data set, right? And which tree would you like to select? Or which tree do you believe is the best? So, yes, exactly right. I think someone has pointed out. I have brought up this point before, right? So basically, we want to pick up the resulting tree to be as small as possible, right? It is kind of satisfy our intuition because our nature, we prefer simplicity, right? If it's not necessary, we won't increase the complexity, right? So the tree, you can view like a number of nodes, number of the branches can be kind of indicator of the complexity of your decision tree model, right? So if you got 10 trees, each of which perfectly represents data, of course, I would like to choose the tree who has the smallest branches, smallest number of branches and nodes, right? I want tree to be as simple as possible. So this intuition formally is called Occam's razor principle. So it's kind of a philosophical principle. It's not a mathematical theory. So basically, it does not mean like you have to obey that. But here, I would emphasize Occam's razor principle is very widely used in engineering and scientific disciplines. Okay. So why? So imagine that you might have some kind of experience, right? In kind of all kinds of electrical or products, right? All kind of products. So we have a common sense that the simpler the product, the more reliable it is, right? The more it performs well in the long term, right? So it's kind of the same issue. It's kind of the same problem here, right? So we want to use the decision tree when we train them or when we construct them from the training data. We want to use them to give prediction for like possible numerous test examples, right? We want to give like on average good accuracy, reliable predictions. That's why we prefer simple trees, because if the tree is overcomplicated, you can't imagine what will happen, right? In some weird cases, might give you very nonsense predictions. Mm-hmm. So you can imagine, right? You might only have like 100 test training examples, right? But when you enumerate all possible feature values, it could be a lot, right? So suppose each feature value takes possible each feature or each attribute takes 3 values. You got like 100 features. How many possible test instances do you have? Like 3 to the power of 100, right? That's many, right? So you use a limited amount of training data to construct tree, but you want your tree to work well, reliable, and robust in like a huge amount unknown test examples. That's why our motivation to have this tree to be as small as possible, right? The smaller the tree you have, the more reliable or more controllable you believe your tree's behavior is, right? And this is, but again, I want to emphasize, this is just a philosophical principle. It's not like some a theory or lemma or a corollary, something like that. And it arises from some philosophy discussion, especially about like gods or something like that. It's about religion. It arises from religion. So, but I don't want to get to that because I'm not expert in that field. But basically, people in like numerous engineering and scientific domains, people have found that Occam's razor principle is really, really useful principle. So the people use them by default to select your models, to design your products, and design your cars, to design your to do manufacturing things, right? So that also is our goal, right? So if we want to construct a decision tree to represent the data, right? Under the same representation ability, right? We want to pick up the tree. We pick up the smallest tree. How do we fulfill this goal? Unfortunately, we find that if we want to create the global minimum decision tree consistent with data, it's very, very hard. It's an NP hard problem. And you can imagine if you want to do that, you have to enumerate all possible orders of the attributes to split on the data set, right? So suppose you have n attributes, then you might have like n factorial possible orders of attributes to split on data set, right? You have a you have to consider what? That's a good question. That's actually it depends on if you have a new set of training examples, right? If you want to, how do you update your tree, right? So there are several choices. You can merge your new coming data set with the old training set and then construct tree from scratch. Or you can construct your tree like incrementally. Both are fine, but it really depends on your application. Like for example, if you have if your computational resource is enough, you might want to construct tree from scratch. If you want to fast update your tree, you might want to do this incremental construction. Okay. So, but here I want to emphasize, right? So if our goal is to create a global smallest tree, then there's comes a computational problem because you won't be able to enumerate all possible orders, attributes, and pick up the one who results the smallest tree. Okay. And then we have to sacrifice some kind of global optimality, right? So we're going to use some greedy heuristic search. So we trade off some kind of like a global optimality for the efficiency. Okay? We want to make some like a trade-off. And the strategy is as follows. So each step, we just look at the current attribute, right? At the current stage, we just look at one attribute. We hope that by using that attribute to split data, we can make the split data subsets of the data to be as purely as possible. In other words, we hope that at every stage, we can pick up currently what is the best attribute. After using that attribute to split on the current data, we can best improve the purity of the labels. That's my greedy strategy. Purity here is a little bit Yeah, but it's not very exact as for now. But we'll discuss it. But you can view like intuitive purity means that, okay, the best purity will be all the examples have the same label, right? But a little bit worse purity will be okay. Majority of examples will have some label, and only a minority of examples have other labels. Yeah, that's purity. I mean label purity. So why is this a good or sensible strategy, right? You can imagine, because every time I pick up an attribute to split on data set to best improve the label purity, so you can expect that after just a few such kind of steps, I can make all the subsets to be uniquely labeled, right? And then we can expect our tree to be small. That's the greedy strategy. Does it make sense? But then emphasize that this is not a global optimal strategy. It doesn't guarantee the global optimal, meaning that, okay, even you follow this strategy, it might give you like a few steps to create a construct tree, right? Every step you're gonna create one more level of the tree, right? So it might give you a small tree overall, but it won't guarantee you a globally smallest tree, right? Because every time you just fix the selection of attributes in the previous steps, you never backtrack, right? You never try backtrack and to look at, okay, if I alter the previously attributes, what will happen, right? I just assume, okay, all the attributes are fixed. All the previous attributes have already been selected and fixed. I'm gonna only pick up at current stage what is the best attribute, right? So it's kind of a locally optimal strategy, and the locally optimal strategy not usually give you the global optimal strategy. So now it's clear that our ID3 algorithm follows this greedy heuristic, right? So if you look at this algorithm steps, right? So we just do it step by step, right? Every time we just fix the attributes that have been used before, right? And on the remaining or the current available attributes, we're gonna pick up the best attribute. Here, the best attributes means that, okay, when I use this attribute to split as, I expect that my purity, label purity improvement is the best. Then I'm going to use this attribute A to split on data set, and then I fix A in my select attributes, and now I call myself to split, to further split the remaining subsets again and again until all my leaf nodes are created. Okay. So the main decision in this ID3 algorithm is the selection of the next attribute to split on. Okay. So then the remaining question is how to evaluate the attribute or feature with respect to the label purity in partitions or in splitted subsets. Okay. So is everyone comfortable at this point? Because it's really, really important before we really look at how to measure this purity and rank those attributes and pick up the best one. Okay. But first, we do need to understand the motivation here. Okay, bear with me. I just want to repeat this motivation, right? So the global, we believe that the best attribute should be the globally minimum tree, right? However, to achieve this globally minimum tree is usually practically infeasible because it's too costly, it's too inefficient. So in practice, we have to make some kind of trade-off. We adopt some kind of greedy heuristic strategy. That is, we just, once we arrive at some step, right, we assume all the previous features are fixed, attributes are fixed. We just look at currently which attribute can best improve the label purity after you use that feature to split. Right? So the rationale is that, okay, if I adopt this local optimal feature selection or attribute selection strategy, because every time I try to best improve the label purity, I can imagine or I can expect that only after a few or small number of steps, all the subsets will be uniquely labeled. Right? That means we are able to arrive at leaf nodes in just a few or small number of steps. Then we will end up with a small tree, overall small tree. That's the whole idea, right? Then the remaining question is that, okay, we need to have some like a quantifiable metric, right, to evaluate the label purity after I use any attribute to split on the current data set. Right? So how to measure that, right? Let us start with some concrete example. Consider a data with two Bloom features, right? Or attributes. It has two attributes A and B. So here are the distribution of those examples. If A and B both are 0, we have 50 examples. All 50 examples are negative. A is 0 and B is 1. We got 50 negative examples. A is 1, B is 0. We don't have any examples. And for A is 1, B is 1, we have 100 positive examples. Right? So now we consider which attribute should we use to split on this data set, right? A or B. We can check that what will happen, right? What are the label distribution after we use each attribute to split, right? If we use A to split, A takes either 0 or 1, right? If we look at A is 0, all the 100 examples here are labeled as negative, right? If A is 1, we found that all the other 100 examples are labeled as positive. So we can see that after we split on A, every subset is 100% purely labeled, right? It's unique label. That's very good. Right? But what if we split on B? If we split on B, when B is 0, we got 50 plus 0 examples which are unique labeled as negative, right? However, we will look at B is 1, right? Here and here, we got 150 examples, but those 150 examples are mixed label, right? 100 are positive and 50 are negative, right? So, and then for this positive B is 1 examples, you have to further split them on A, you get all the purely labeled subsets, right? So now, based on this result, which label should we use? Which attribute should we use to split on data set? A, right? Because obviously, after using A to split on data set, the label purity is much better than the label purity of using B to split on data set. But this is quite intuitive and straightforward. Right? Now let us look at a little bit more complicated cases. Right? What if we have A is 1, but B is 0? A is 1, B is 0, but we have three negative examples. Right? So basically, we have here right? The distribution of examples is as follows, right? In the previous case, we only have 0 examples for A takes 1, B takes 0. But now we have 3 negative examples for A is 1, B takes 0. Now, if we want to compare A and B, right, in terms of label purity, let us take a look. Right now, if we use A to split on data set, for A is 0, is here, and is here. It's still 100 negative examples, which are uniquely labeled as negative, right? However, when A takes 1, right, it's here and here, we now have mixed labels, right? We have 100 positive examples and 3 negative examples. For comparison, let us try to use B to split on data set, right? So if we use B to split on data set, when B is 0, we got 53 negative examples, which are uniquely labeled, right? And when B is 1, we got again 100 positive examples and 50 negative examples. So now we can see that using either attribute wouldn't give you a unique labeled subsets. but I still want to compare which one is better. So now, will you please tell me which one do you believe is better? A, I heard A. Any other suggestion? Yeah, your intuition is right? We still believe A, right? Why? Because although both this positive left subset in A and the left subset in B are mixed label, right? But you can see in terms of purity, the purity, label purity here is much, much better than label purity here, right? You can see that, okay, like 100/3, like you can will like nearly 97% or 98% of examples are positive. Well, this is kind of only like 2/3 are positive. In terms of label purity, of course, the result of splitting on A is better than the result of splitting on B. Right? So you can see that even we have not matched the ideal case where, okay, using A, you can give all the examples, all the subsets to be unique labeled. You can still able to tell which one is better, which one is worse, right? And now the question is, how do we quantify this, right? Because we need to tell the algorithm, okay, for example, this label purity might be 0.9, this label purity would be 0.2. Of course, 0.9 is bigger than 0.2, so I choose A, right? I need to have some quantifiable metric. So which quantifiable metric we're going to use, right? They actually have different choices. And here, we're going to start with this heuristics called information gain, which is used in the original ID3 algorithm, and is also the most popular label purity measurement of label purity measurement. But later we're going to discuss some other very useful and common used measurement. They can all plug into this ID3 algorithm framework. So information gain is based upon this information theory term. It's called entropy. So how many of you have heard of entropy? Oh, that's good. That's good. So entropy is really used to measure kind of uncertainty. Right? So you can imagine if you have a set of examples and they are mixed label, right? So the entropy is a measurement like how you feel uncertainty about the labels in these examples. So like if your examples kind of like half of them are labeled as positive, half of them are labeled as negative, actually I'm mostly uncertain, right? Because give me an arbitrary example, they have half a chance to be positive, half a chance to be negative, right? You're most uncertain about their label. However, if all your examples are labeled as one, like positive, right? And now you pick up an arbitrary example. You ask me, how do you feel their label? I can tell it's positive. I'm pretty confident because I know all the labels is the same, right? It is positive. Right? So how do we compute entropy? So given a set of examples S, right? Each example has taken a binary label, either positive or negative, right? The entropy of S is computed as follows, right? So it is minus P positive logarithm P positive subtracted P minus logarithm P minus. So P positive is the proportion of positive examples, right? And P negative is proportion of P negative examples, right? And the entropy is defined not only in binary labels, it can be extended to like multiple categories, right? Suppose you have a discrete probability distribution with k possible labels, where the probability that your example takes each label is p1 to pk, then the entropy is given by this. So it's basically a negative summation of each probability pi times logarithm pi. Right? So what's the property of entropy? This is a very important. Actually, I have just discussed about it. If all the examples belong to the same label, then entropy is simply 0. Right? So we can just verify this, right? If, for example, if it is a p positive is 1, right? So you can see this 1 logarithm 1 is simply 0, right? But someone may feel like, oh, feel confusing, like, okay, p minus 0 and 0 times log 0 seems ill-defined, right? And here, in the information theory, people will this 0 log 0 as 0. So you can view like this is a limit. This is x logarithm of x when you take a limit when x approaches 0. So it's a straightforward to show that this limit is always 0. So so by taking this get around this ill-defined things, right? We can have the conclusion that if all the examples belong to the same label, the entropy is simply 0. And when p plus p minus equals to 0.5, the entropy is 1. And we can show that this entropy is always non-negative. That actually tells us the more even your labels are distributed, the larger the entropy. Right? The more biased your labels, like p positive could be 0.8 and p negative 0.2, then the smaller the entropy. So you can see that this blue bars shows the entropy value, and this two black bars shows the p positive and p negative, right? So you can see that when p positive and p negative is the same, then you have the largest entropy. However, when p positive and p negative is kind of like more and more biased, your entropy keeps decreasing. And if p positive is 1, p minus is 0, or p minus is 1, p positive is 0, you have the 0 entropy, which is the smallest. Okay. This is actually consistent with our intuition about uncertainty, right? So if your positive and negative examples are same, have the same number, you are most uncertain about the labels in your data set, right? Because they have half chance to be this and half chance to be that. You cannot tell anything. That's, in this case, you actually have the maximum uncertain about the labels, right? On the other hand, if your labels are highly biased, right, 99% are positive, only 0.01% are negative. Like, giving you an example, like, you can say, okay, I'm pretty confident it should be positive because I know that 99% are positive. So you're much less uncertainty. You're much less uncertain about label. Okay. So in the extreme case will be, okay, I know that p positive or p negative is 1, meaning that, okay, I know all the examples are either positive or negative. Then you have least uncertainty about your labels. Okay. Does it make sense? That's where this that's how this entropy is defined. This measures your uncertainty about the labels in the data set. Right? And this definition also applies to the multi-class or multiple labels. Right? If you have a k possible labels, it can be showing that the uniform distribution has the highest entropy, namely all P1, P2 to Pk equals to 1 over k, right? Has the largest entropy. However, the more biased the distribution of those labels, the smaller the entropy. So again, if you have like some particular category, like say P1 equals to 1, all the others 0, your entropy will achieve the minimum, which is 0. Does it make sense? Is everyone comfortable with this definition? Right. So now we can associate the entropy definition with the purity. Right? So as we just mentioned, right? High entropy indicates a high uncertainty, right? So what causes high uncertainty? The low purity, right? So imagine for the binary labels, you got 50% positive labels, 50% negative labels, right? So you got least purity. You got least label purity, And at this stage, you got highest uncertainty about the labels. Right? So it gives us this correspondence, like high entropy indicates high uncertainty, and high uncertainty is caused by low purity, meaning that those labels are more evenly distributed. Then it gives you more uncertainty about the labels because everyone has roughly the same kind of like chance, right? So at this case, it's most difficult to tell. Okay, this example could belong to which label, right? On the other hand, low entropy indicates little uncertainty, and little uncertainty is caused by the high purity of the label. Right? I take the example just discussed, right? If you have 99% of examples are positive, only 1% is negative, right? That means your label purity is quite high. Right? At the same time, you are much more confident about labels. You have least uncertainty. Not least, but you have very small uncertainty about labels in your data set. Right? Does it make sense? Okay. So our information gain is defined based upon the entropy, right? So as we mentioned, right, high entropy corresponds to a low purity, right? And low entropy corresponds to a high purity, right? Low entropy means low uncertainty. Low uncertainty corresponds to high purity, meaning the labels are more biasedly distributed, right? So as we mentioned, right, our strategy to select attribute is to look at, after using a particular attribute, how much increase of the purity you can get, right, after you split on this data set with A. Right? So the increase of the purity can be viewed as reduction of the entropy. Right? That's the correspondence. Right? Let me emphasize this again. Right. So high purity, high uncertainty measured by high entropy corresponds to a low purity. Right. And low uncertainty corresponds to a small entropy corresponds to a high purity. Right? So you want to improve the purity, we actually measure the reduction of the entropy, right? So it's kind of like opposite direction, right? So now we can define or measure the increase of the purity by looking at the expected reduction in entropy caused by partitioning on this particular attribute A, right? Does it make sense? Right? So, so how can we compute that, right? So given this set S, right, set of examples S, and we look at the information gain of using A to split on S, right? It is defined as, first, we're going to compute the overall entropy of the S set S itself, right? S is a set of examples. Then we'll look at the entropy of each subset using S, using A to split on S. I remember A can have multiple values, right? And SV, meaning the subset of examples in S whose entropy A takes value V. Right? We can compute the entropy of each S of V. Right? Now we're gonna reweight this entropy according to the size of the SV. And we take a weighted average as our expected entropy after using A to split on S. Right? Now we'll do this subtraction, or we subtract S by this expected entropy. We get our information gain. So again, this measures, okay, before we split on data set S, right, with A, what is the global uncertainty? About the labels in S, right? Now I use A to split on S. I got a bunch of subsets, S1, S2, S3, right? And each subset has their uncertainty about their labels, right? I take the weighted average and I do the difference between them. It tells me what is the expected reduction of the uncertainty of those labels, right? After I split A with A, I split S with A. Okay? As we just mentioned, this reduction of entropy indicates the improvement or the increase of the purity, right? Does it make sense? Does this formula or does this definition sounds reasonable? Okay. Any questions so far? Gini index. I think I think you're trying to beyond what you want to discuss. Yeah, we're gonna come to Gini index later. Yeah, but I mean, as I just emphasized, like to measure the purity is not only in terms of entropy. You can have other measurement as well. We're gonna talk about majority error. We're gonna talk about Gini index. But here I want to start with the classical popular measurement called entropy. And then is like, you know, uncertainty or entropy and the purity is kind of like two sides of one coin, right? The large uncertainty of entropy means the small purity or low purity, right? And the small purity, the small uncertainty or small entropy corresponds to the high purity, right? So if you don't look at increase of purity, you actually look at the reduction of the uncertainty or reduction of the entropy. Right? That's why we define it in this way. Right? So here I want to explain why should we reweight the entropy of each subset after using A to split. Right? This actually matters the size, right? Consider you use A because A can take different values, right? So that means different subsets may take different sizes, right? If you have 100, if one subset take like only 10 examples, the other subset only takes 100 examples. So which one is really more important in terms of purity? The larger size, right? Even like those 10 examples are purely labeled, but for those 100 examples, they're highly mixed. This is not very good, right? Would rather choose like someone like give you like 100 examples to be much purely labeled, much more purely labeled, and these 10 examples are relatively less purely labeled. Right? Why? Because you can imagine to further split down this 100 examples subset, you have to create more branches and nodes, right? So our overall goal is still to make the tree to be as small as possible, right? So of course, the better purity of this larger subset actually matters more than those small subset. That's why we reweight those entropy of each subset according to or proportional to its size. Does it make sense? Is everyone good for this? Yeah, and by the way, I have to emphasize, when you do the reweighting, don't forget to divide the total size of S, meaning that this weight is kind of a probability between 0 and 1. It's normalized to their summation to be 1. Otherwise, it won't give you the right result. Okay. So entropy of partitioning the data is calculated by weighting the entropy of each partition by its size relative to the original set. Then we get our information gain. We rank the attributes in terms of information gain, and the attribute who gives the largest information gain is viewed as who can best improve the label purity after you use that attribute to split the data set. And then we're going to use that data set, use that particular attribute to split a data set. And then we call ID3 again, and then every time we just rank the information gain of each available attribute on the current data set. Okay? So we're going to use this information gain principle in our IB3 algorithm to showcase how each attribute is selected to partition data set and how the tree is finally constructed on Thursday. Okay, see you on Thursday.